Hello, my name is Otto Alves and this is a short presentation about my master's thesis titled A Deep Learning Approach for Spatiotemporal Interpolation of GNSS-R Soil Moisture Retrievals. It was defended in May 2024 at the UVIN and was supervised by Professor Wolfgang Wagner. The work contained in this thesis was conducted in the context of the GNSS project, which is a part of the European Space Agency Scout program. Starting out with our motivation. So first of all, what is soil moisture? Well, it's basically the water content of the soil and a key variable in agronomy, climatology, and the earth sciences. In the recent decades, radar sensors aboard Earth observation satellites have allowed us to have a global, near real-time monitoring of soil moisture. However, several flagship soil moisture monitoring satellite missions will be discontinued in the next few years. And in this context, Global Navigation Satellite System Reflectometry, or GNSS-R, has emerged as a promising and cost-effective alternative. It uses receiver-only satellites to capture signals originally transmitted by navigation satellites and then reflected off of the Earth. Those signals carry information about the soil moisture of the reflecting surfaces. In this thesis, we are working with soil moisture data from NASA's Cygnus mission, but in preparation for ESA's upcoming GNSS mission. GNSS-R soil moisture is still experimental and faced with complex issues, such as that of spatiotemporal data sparsity. For instance, on the left, we show a map of soil moisture data collected by all 8 Cygnus satellites over the course of a day. On the right, we show daily data collected by only 2 of the 8 Cygnus satellites, roughly simulating the coverage of GNSS, but at a narrower latitude range. So, moving on to our actual research problem. So what is spatiotemporal interpolation? Well, it means gap-filling the missing data points by leveraging the known observations from its spatiotemporal neighborhood to produce a seamless, gap-free dataset. This can be framed as a regression problem, where the missing values are the targets and their respective neighborhoods serve as the predictors. The state-of-the-art for this task is the POBI algorithm, which is very successful but has some drawbacks, mainly to a location-centric design. POBI trains a location-specific and non-transferable regressor for each pixel, which requires high computational resources. Since each of those regressors is modeling what is essentially the same physical quantity, in our case soil moisture, it follows that there should be a large overlap or redundancy in the dynamics that they must learn individually. To address this redundancy, we propose a method called Neurospatiotemporal Interpolation, or NSTI. It consists of using deep learning, in this case specifically convolutional neural networks, to develop a unified and compact model applicable across all pixels, capable of understanding both global and local soil moisture dynamics. Our research question then is deep learning, specifically supervised deep learning with CNNs, a viable tool for spatiotemporal interpolation of Cygnus soil moisture retrievals, and how does it compare to POBI in the same task? Zooming into our methods, we start by organizing our observations in data cubes, which are n-dimensional arrays or tensors, whose dimensions have some sort of spatial or temporal semantics. We define a scenario with 2 data cubes, the input data cube containing data observed by only 2 of the Cygnus satellites, and the output data cube containing data observed by all 8 of them. We then identify all cells that are empty in the input data cube but filled in the output data cube, and then we form input-output pairs, where the input vectors are the data volumes of the spatiotemporal neighborhoods of the empty cells, along with optional ancillary data, and the output vectors are the known soil moisture values from the output data cube. Finally, we conduct the standard supervised learning pipeline, splitting the dataset temporally into train, test, and validation slices. We also train POBI on the same data split, and then it serves as a benchmark for NSTI's performance. Regarding the results, we will first show a brief qualitative overview. Here to the left, we can see a daily time slice of the input Cygnus soil moisture data cube interpolated with the trained POBI model, and to the right, the same time slice was interpolated with NSTI. In a visual sense, we can see that NSTI seems able to capture the same spatial patterns as POBI, reconstructing the same geographic patterns in the soil moisture data. Moving on to a quantitative evaluation, we see that NSTI has achieved a slightly lower RMSE than POBI when trained and tested on the same data. While this difference is statistically significant, we refrain from making any strong statements about surpassing the state-of-the-art, as this gap may reasonably be closed or even reversed with sufficient hyperparameter tuning. But notably, NSTI is able to do so while using a model that is far smaller than that of POBI. For a 9 km spatial grid, NSTI is about 2 orders of magnitude smaller, requiring much less storage and memory overhead. To wrap it up, we conclude that NSTI achieves a performance comparable to that of POBI, the state-of-the-art algorithm, while addressing some of its drawbacks, especially model size and memory overhead. With upcoming GNSS-R missions, we expect this framework to support the development of deep learning-based interpolation models that enhance both the quality and usability of novel soil moisture data products. In particular, for GNSS, techniques like transfer learning could be applied soon after launch, reducing data sparsity even in latitudes not covered by any existing GNSS-R data record from Cygnus, something that would be a requirement for POBI but not for NSTI. That is all for today, and thank you for your time.